Hello everyone. In this session, we are going to see the measurement in battery management system. We all know that how important is the measurement for the BMS. Measurement is the foundation of any battery management system. Without accurate measurement, we cannot prevent overcharge or overdischarge. Voltage measure ensures that each individual cell remains within the safe limit, and current measurement allows accurate state of charge estimation and power limit calculation. Temperature measurement guarantees safe thermal operation. So, measurement directly determines safety, performance, efficiency, and battery lifetime. Now we are going to see how we are going to measure the cell voltage. Now, cell voltage measurement. In large format lithium-ion systems, each series connected cell must be measured individually. Okay, unlike the lead acid batteries, we cannot rely on a total pack voltage. Cell may differ in capacity or state of charge. Okay, the measurement circuit must present very high input impedance to avoid draining the cells. Okay, parasitic current must be minimized, especially in standby mode. Fine. Active mode current may be higher during the measurement, but passive current must be extremely low to prevent long-term over discharge. So, here in voltage measurement, redundant voltage measurement is also important, where in the safety critical systems, redundancy must improve reliability. Okay, now there are symmetrical and asymmetrical, where symmetrical Dewar measurement means two equally accurate measurements. Asymmetrical measurement means one primary accurate measurement and one backup. Okay, for highly critical application, triple redundancy may be required. However, redundancy will increase the cost and complexity. So the measurement architecture must be selected after proper fault-free analysis. Okay, now we are going to see measurement accuracy and SOC error. Okay, now SOC estimation error depends on mainly two factors. First, voltage measurement error. Okay, second one is slope of the SOC versus open circuit voltage curve. Mathematically, SOC error is proportional to the voltage error multiplied by dSOC by dV. If the open circuit voltage curve is flat, like in LFP chemistry, even a small voltage error causes large SOC error. If the curve is steep, SOC estimation is more robust. Okay, in modern BMS ICs typically provide accuracy better than 10 millivolt. Okay, now here this graph we can see. In this graph, we can see how voltage measurement uncertainty creates a range of possible SOC values. Okay, where the voltage or slope is steep, SOC error is small. Here you can see SOC error is small. Where the slope is flat, okay, SOC error increases significantly. This shows why chemistry selection influences measurement requirement. Okay, and coming to this dSOC by dV versus SOC, where this graph shows how the slope changes with SOC chemistry. Okay, we can notice that the slope varies significantly across the SOC range. In some regions are highly sensitive to the voltage errors. Therefore, voltage measurement accuracy must be tailored to the battery chemistry. Okay, now we are going to see what are the measurement faults. Okay, here in voltage measurement faults, there are several possible failure modes. Okay, a multiplexer may measure the wrong channel. Okay, a constant but incorrect voltage may be reported. A cell interconnect failure may cause a subgroup to appear normal while disconnected from the string. Okay, to detect faults, we compare the sum of cell voltages with the total pack voltages. Okay, now here this is essential to prevent severe overcharge and over discharge. Fine. Now we are going to see how we are going to measure the current. current measurement in BMS. In a series battery string, okay, one current measurement represents the current through all the cells. Okay, current measurement is required for SOC estimation, overcurrent protection, and power limit calculation. If the current sensor has offset error, SOC estimation will drift over time. In safety critical systems, redundant current sensing may be required. Here you can see shunt based current measurement. A shunt is precision low value resistor. Okay, the voltage drop across it is proportional to the battery current. Kelvin connection is used to eliminate measurement error due to contact resistance. Okay, here we can see the Kelvin connection diagram. In Kelvin connection, a separate terminal are used for current flow and voltage sensing. This ensures that the measured voltage represents only the sent resistance and not wiring resistance. This significantly improves the accuracy. Okay, now this shunt for current measurement, what you are seeing in this figure, these are examples of current shunts. Okay, they are robust and highly accurate, typically between 0.1% to and 0.5%. However, they introduce small power loss and are not electrically isolated. Okay, now what we are going to see the Hall effect current sensor now. Okay, now here Hall effect current sensor, which measures magnetic field generated by the current. They provide electrical isolation between measurement circuit and the high voltage battery. Here you can see in the diagram, in this sensor, the conductor passes through the sensor body. The magnetic field is detected internally and converted into voltage. Hall sensor require external power. Okay, offset error is a major concern because it accumulates over time in SOC estimation. Zero offset calibration during no current condition is recommended for this sensor. Okay, now coming to this current sense measurement. Okay, here ADC resolution alone does not guarantee the accurate current measurement. The entire signal chain must be optimized. For shunts, the signal is in millivolts and highly sensitive to the noise. Okay, here twisted pair wiring reduces electromagnetic interference. Okay, the sampling rate must be satisfy the Nyquist criterion, at least twice the maximum frequency component of the load current. Fine. An analog multiplier removes unwanted high frequency noise. Active filter must avoid DC offset because offset accumulates during the integration. Okay, where using the precision or ratiometric voltage references reduces the reference related errors. Okay, where high common mode rejection ratio is essential, especially in shunt circuit. Fine. In internal sensors, save space but may complicate the PCB layout. Now, the multi-range sensing improves integration accuracy for wide dynamic current ranges. Here you can see in the block diagram, this block diagram shows the full measurement chain. Sensor, okay, isolation amplifier, ADC and digital processing. Error can occur at every stage. Therefore, focusing only on ADC resolution is not sufficient. Okay. Now coming to this synchronization of voltage and current. Now, for advanced algorithms like impedance estimation, voltage and current must be synchronized. If measurements are not aligned in time, dynamic calculation become inaccurate. Okay. Three approaches are used for this. First one, simultaneous sampling. Okay. Second one is time step based synchronization. Then interpolation. Proper synchronization improves the model based estimation method. Okay. Now coming to temperature measurement. Here temperature strongly affect battery safety and performance. We know that. Okay. Now NTC thermistors are most commonly used. thermistors, where typical operating range is minus 32 plus 65 degree Celsius. Okay, where self heating must be minimized by limiting current through the thermistor, where proper sensor placement is critical because we measure surface temperature, not internal core temperature. Okay, now we are seeing here resistance versus temperature graph. Okay, this graph shows the non-linear resistance and temperature relationship of an NTC thermistor. Okay, resistance decreases rapidly. Okay, as the temperature increases. Because of this non-linearity, lookup tables with interpolation are prepared over simple linear equation. Okay, now what are these measurement uncertainties? Okay, here you can see all measurement contain uncertainty. Right? The source include sensor tolerance, ADC error, temperature drift, wiring register, and calibration errors. Okay, worst case circuit analysis must be performed for this. Okay, now BMS algorithm must tolerate uncertainty without compromising the safety. Okay, now the measurement forms the backbone of the battery management system. Okay, where accurate voltage prevent overcharge and overdischarge. Accurate current ensures reliable state of charge estimation. Accurate temperature guarantees safe thermal operation. Careful hardware design, filtering, synchronization, and fault detection are essential to ensure robust BMS performance. Okay. In the next lecture, we will discuss the battery management system functionality. Thank you.